recording, okay? And then we are going to start sharing screen. Hold on, let me find it. Okay, here. This one. So we are going to continue our discussion about dimensionality reduction. You remember we learned. So this unit is about dimensionality reduction. And for this, there are a number of ways to do it. That yesterday we also kind of reviewed. And one of the approach is general, we call it feature extraction. And in this unit, we learned two approaches for data feature extraction. Do you still remember what are those? Who still remember? You can, yes. Do you remember we discussed in this unit two approach to do feature extraction? Who remember that? One is start with P, the other start with L. Do you remember? This is PCA.
PCA and LD.
Yeah, very good, very good. So how about like this? Right now, so Raw, you answered, is it? So can you also send to the chat those two answers? So from now on, anyone answer the question, I will give you bonus point, okay? So, and the feature example, so PCA and LDA, is it? Yeah, so for PCA, let's just do some review, okay? And for PCA, do you remember last time we discussed that example about MNIST? And who still remember the MNIST example is about what? This is very traditional, okay, example in machine learning, the data set. A very classic data set. MNIST. Who still remember that? That MNIST? So from now, like we said, okay, if you answer a question, you get a bonus point. MNIST is about what? You remember in this unit, last two class, we discussed about the data set. Do you still remember what the data set is regarding? You see here, for this, the one that we are going to discuss today, the CSV, that file is about wine. So this is going to be about wine. Then my question is, how about the MNIST? Who still remember that? MNIST is about, let me just give you some hint, image. Do you remember what kind of image? Who remembers the image? What kind of image? It's about what? It's about digit, is it? Handwritten digit. Digits, is it? So total class in that example we have is what? Is 10 classes, is it? So it's a handwritten digit from 0 to 9. Is it? Is from 0 to 9, is it? That's regarding that MNIST data set. Okay, so we have a new one just joining. So just for you guys information, okay, so starting from today, if in class you answer any questions, I will give you bonus point, okay? So right now, what we are discussing is about the last two classes we discussed the MNIST example, MNIST data set, is it? And we apply the PCA on the MNIST data set. And I'm just trying to review because I really hope you can remember this MNIST classic data set, what it is about. Is it, like I just explained, about handwritten digits, is it? And so it's for classification, and we use logistic regression, is it, to do classification. And there are 10 classes, is it? And can you then tell me for the PCA? So PCA, it's used for feature extraction, is it? So basically, more general, it's about dimensionality reduction, is it? So then in MNIST data set, if we apply the PCA to MNIST data set, what else? What other benefits we can get? So the question is, PCA is used for dimensionality reduction, is it? So based on this dimensionality reduction, what other benefits we can achieve besides to help training data?
Compression.
Yeah, very good. Yeah, you can send the answer, okay?
Okay.
And then I will give you bonus point, okay? Besides helping learning, is it model learning? Is for what? Is compression, very good, yeah. Compression, is it? And especially for the
Speeding
MNIST.
up the algorithm.
Yeah, please.
And it also reduces memory or stores data.
Yeah. It helps to, because it uses less storage space, is it? So that's why we call it compression, is it? You compress, especially for image and audio data, is it? And it's just the quality, it's just impact the quality, is it? But if you can compress data, is it? It's still readable, is it? So it depends on what kind of situation, if you need high quality or low quality, is it? And in this regarding, you compress the data, is it? And can still help model learning, is it? And we did see, is it? So because this is not a very so the dimension is not that high because it's just 28 by 28 pixels. So the original is 784 features. Is it? Features means you have this number of columns. Is it? And then in our example, we said if we apply PCA, is it? If we apply PCA with 95% of explanatory, 95% of total explanatory, is it? You can achieve, you can reduce the feature, is it? The feature space can be reduced to feature space can be reduced to 154. You remember that example, is it? So the columns, when you do the training, is it? So the features reduce quite a lot. Then definitely it can expedite, is it? Speed up learning. Is it with logistic regression? Is it can speed up the learning? Is it with less features? Is it? But it didn't impact the performance too much. Is it? We can still achieve over 90% of accuracy. Is it? So that just shows, is it, with dimensionality, is it, a lot of time it's quite useful. Is it, that's regarding PCA, okay? And a review is PCA. So PCA, it can achieve the dimensionality reduction. Reduction, is it based on what? The goal is to what? So the goal with PCA is to what? Is to maximize. Do you remember maximize what for PCA? Is to maximize, remember this word, okay? Variance.
Variance.
Yeah, so variance, generally speaking, regarding our data set, is about what? It's about the spread out. Is it of the data? Of your data set? Is it of the data set? And the goal is you try, because you remember, initially, suppose this is the feature, is it? And you have data, maybe something, is it? I didn't draw very well. Okay, let me do some erase work. Erase. Let me kind of erase this part. Okay. Erase this part. Okay. And let me do back draw. Okay. So the goal is to what? Is to find this new axis. Is it? So this is called a principal component. Is it a principal component? And if you project the data, is it to this principal component? Is it? And you see, you can quite easy to do classification. Is it? So just with this single component. And previously you have two, x1, x2, is it? And right now if you pick one component, it can project and you can still classify, is it? And you can also see, visually see the data spread out the most along this component. If you measure versus the original feature, the data spread out, is it? This is the most spread out one. That's why we said to try to maximize variance. Okay, so that's the goal of PCA and why it can achieve the goal. So with PCA, a lot of time it helps to what? To reduce noise. Is it reduce noise? Is it because you're trying to maximize the variance along the principal component? Okay, so this is PCA. And the last class, we also learned LDA. Is it LDA? So for LDA, it's linear discriminant analysis. Is it? And it can also reduce feature space. Feature space. Is it? And here we said reduce feature space. Does it mean that you remove some features? So both PCA and LDA can reduce feature space. Is it? Does it mean you remove some features?
Reduce dimensions.
Yeah, very good. Okay, so it doesn't mean you're going to reduce feature, is it? You're going to apply some, we call it linear transformation. Is it transformation? Then you're going to have new feature space. And this new feature space, its dimension, is less than the original feature space. Okay, because it's not the original feature, is it? Because over here, this is original feature x1, x2, is it? And over here is your principal component, is it? That component. And this component is not x1 or x2. Is it? It's some kind of transformation of both x1 and x2. Is it? So it's a new feature. It has, is it? But it has some relationship with the original x1 and x2 feature. Okay. So in this regarding, it's not remove feature. Is it? So that's why we said feature dimensionality reduction. So if you use this PCA and LDA, is it? It's called what? It's called it's called what? It's called a feature extraction. Is it? You extract the most relevant features, is it? And you transform them to new feature space. Okay, and if you remove some feature, that's another category, dimensionality reduction. Who remembers what that is? And Ron, you can also add another, the previous answer you add,
Oh,
and
okay.
yeah, the other one, then the dimension, I remember you said that it's reduce feature space, yeah. So I will also give you bonus point for that. And who then remembers what kind of approach we can achieve to remove features? Remove some feature, who remembers? Generally speaking, feature dimensionality reduction, we discuss feature extraction as one approach. What is the other general approach?
The linear transformation.
What is that?
Linear transformation.
No, it has nothing to do with transformation. For transformation, both PCA and LDA will do transformation. It apply mathematics coordinate system transformation, etc. But the other one, you remove feature that you don't need any transformation. It's purely based on, suppose original you have a feature x1, x2 to xm, etc. Then you're going to throw away some of the feature and keep some of the feature. Is it? Keep the important features. And how do you know which feature is important, which feature is not important? Who remembers? That approach? You remember, we needed to know of those basic performance improvement approaches, okay, in machine learning. Someone answered. Let's see. Feature importance. Yeah, feature importance. Very good. Yeah, very good. Feature importance. Okay. Yeah. So feature importance, and it belongs to what category? The name. Here it's called feature extraction. We have another called feature what? It's also two word. Feature what? Because you keep important features. Is it, as the answer in the chat said, it's called feature importance. Is it? You pick important features through feature importance. What that is called? It's here's a feature extraction. What's the other called? Feature S, starting with S.
Selection.
Very good. Selection. Yeah, you can put your answer, okay, to the chat. Yeah, feature C. Remember, okay, it's called feature selection. Okay, so through that feature importance, you select important features. Is it? And you filter out. Is it? You remember we apply that random forest. Is it? Using random forest, you can select the importance of features. Is it? Yeah. So this is called feature selection. But LDA and PC, it's not. Okay. Because for feature selection, you are not going to change original feature. You're going to keep them. Is it you're going to keep them? You just throw away some of the features that's not important. Is it? But for this feature extraction, you need to apply the math. Is it quite a comprehensive math calculation? Is it called eigenvalue? Eigenvector. Is it you're going to apply, you try to find the eigenvector. That's quite a comprehensive topic, is it? So you use that to find a new feature space. Is it? So it's involved transformation, okay? So we need to get all of this kind of concept clear, okay, regarding dimensionality reduction. Because this kind of concept, even though with deep learning, like convolution neural network, CNN, yeah, why we need CNN, so later on you will also see that, okay? So this kind of concept, we need to understand it, okay? Okay, so here we discussed the feature extraction. Is it through eigenvector that do some math transformations to reduce feature space? Is it? And then to deal with nonlinear approach learning. So nonlinear learning models, is it? And what kind of techniques? What kind of technique you use to make nonlinear models still be able to be classified by some linear model, like SVM and PCA. PCA is not for classification, okay, but we can also, because generally speaking, PCA is also going to do linear transformation, is it? But for nonlinear, for the data set, I shouldn't say nonlinear model, I should say nonlinear distributed that's also not a very good word. So it's based on the non-linear, yeah. So learning model is good here. Yeah, it's good.
Covariance matrix.
Pardon me?
Covariance matrix?
No. What do you mean co-index matrix?
I mean, we like you. What do I say?
No, the idea is, suppose you have data distributed like this, is it? So those is one category, is it? The other category kind of distributed. Then if we want to do classification, no matter you apply logistic regression, it won't work directly on it, is it? Or you use SVM, it won't work, is it? Or you say, oh, we use perceptron, is it? Adeline, is it? It won't work directly, is it? So we need to apply some technique, because visually you can clearly see it's separable, is it? It's two class. It's very straightforward, is it? But if you ask a machine to do it, if you directly apply logistic or SVM, because both the starting point is linear.
Oh.
Remember what's the technique?
You mean kernel PC analysis?
Yeah, very good. So that technique, we call it a kernel. Okay, you can write this and I give you bonus point, okay? So that's a kernel techniques. Is it? Kernel technique is what? It's kind of, okay, let's erase this part, okay? So it's what? Is because original, this is two-dimensional. Is it? This is two-dimensional. Is it? Then you are going to do what? You can convert this, is it, into three-dimensional. Is it? And then you can kind of, okay, so this is kind of, I'm not too good at drawing this, is it? So something like it, and then for the other one, is it? And so the height is going to be different, is it? So suppose this is X, Y, and this is Z, is it? So the data set is going to be, if you project it into this new one, is it the height, then they are separable, is it? So if you can come up with some function, is it, to do the transformation, is it, so that you can have of one class in one height and the other class in another height, then it's easily separable, is it? Then if you apply logistic regression or SVM, is it, those linear approach, it's then separable, is it? So it's called a kernel technique, is it? So kernel technique, then it's to, so the question is kernel technique increase feature space or decrease feature space? So you're going to
increase feature space.
Very good, super good. Okay, so you can write the answer to this. So it's, you're going to increase feature space, is it? From 2D to 3D this time, is it? But after you do this kernel technique, apply the kernel technique, is it, on the data set, then it's linear separable, is it? So this technique is called the kernel technique. And so the kernel function, is it? And the purpose of the kernel function is not just to transform the original data, is it? Because in PCA, is it? In PCA, you are going to calculate the variance matrix, is it? And if you apply the kernel to every single data set, and then you find each sample's variance in this new feature space, and then you do calculate, it's too much of work, okay? It's not efficient. So what it does, it applies that kernel function directly to the covariance matrix, okay? So that can simplify a lot of work, okay? So this is the concept regarding kernel technique. So keep that in mind. Okay, it's to increase feature space. Okay, and the purpose is not for the to speed up calculation. Okay, so here the purpose is not to speed up. Here the purpose is what? So after you increase feature space, is it? Then you can apply linear approach. Otherwise, those linear approach is not applicable. Okay, but basically this kind of data distribution, you can still linear separable them. Is it linear separate them? It's just you need to find a new feature space, a new feature axis, so that it will be separable along that new feature axis. Is it? So you increase feature to apply so that you can apply linear approach. Okay, so this is the basic idea for kernel. Okay, so just remember, it's not always we're going to do dimensionality reduction. Sometimes we increase dimensionality, okay? But the point is to apply linear approach, okay? Okay, so that's the basic idea. So let's take a look at another example, okay, in this unit about dimensionality. So this time it's not the MNIST data, is it? Oh, just going back. With the MNIST, so we apply PCA, is it? And with PCA, we can also do image compression. Is it? Image compression, but your image is still recognizable. Is it? It's just the quality changed. Is it? With low quality. Is it? But it's still recognizable. Is it? That's regarding that MNIST, the handwritten digits. Is it? Then you can see it's not just going to apply to handwritten digit. Is it? A lot of other kind of image recognition, if you train using the same model to train, you can still make it. Is it? So that's one way to do image recognition. Is it? But this applies to not too comprehensive, not too high definition. Is it? Image, because if your image is a lot of time of image is 20 by maybe 248 by 248, is it? Maybe a much larger high definition, is it image? Then if we apply this, and if you have maybe millions of images you want to train, is it? Then even though you apply PCA, that may take forever. Okay, so that's why later on we will, in deep learning, we will see convolution neural network. Okay, it's also try to find some way to speed up image recognition. Okay. So anyway, that's regarding that example. Okay. So just remember those classical data set that will help you when you do machine learning application development, so that you can see, oh, what is the best approach to achieve that. But like it's also depend on your data, the number of features, is it? So like those MNIST, it's kind of simple image, is it? If your image is too comprehensive, even though you apply PCA, then with logistic regression or SVM, those traditional classical machine learning method, it's still not, it's still going to be extremely slow. Okay, that's why recent number of years we have deep learning concept, okay, to deal with huge data. So anyway, this is another example. So the data set also size is not huge. Okay, it's about wine. Okay, and the columns, the data set columns it has is what kind of wine it is. Okay, then it's some features. Is it alcohol, ash, and all features, 13 features, I remember. I remember previous unit, we also saw this example, is it? Okay, so let's see. Okay, so you're going to split data, is it? Nothing new here. And you remember with regarding PCA, as you better also standard scalar. Is it? So another approach, we did data pre-processing. Pre-processing is, we discussed there are two approaches to do data pre-processing. Do you still remember what are the two approaches you did data pre-processing? And over here, it's at the standard scalar. So what's the goal for this? So data pre-processing also involves a number of factors you need to think about. Is it? So basically, dimensionality reduction is part of data pre-processing because it's not model learning yet. Is it? Because data pre-processing is what? You try to clean your data. Is it? Clean data for, so get the data ready for model learning. Is it? So there are a number of factors you need to think about. Is it? One of it is also deal with, you remember, missing data. How do you deal with missing data? Do you still remember? So those net data in NumPy, how do we clean them? What approach you deal with missing data if your data set has some missing data? And plus, sometimes you have a string type of data. And with machine learning, it cannot directly deal with string type of data. Is it? Because it uses NumPy. Is it array? So how do we get around with this kind of problems? Do anyone remember that? So missing data or string type of data? Missing data, how do we deal with that? You need to know this, is it? Because just think of, if you want developer application, machine learning model, generally speaking, is you scrape data from somewhere, is it? Or like a lot of time right now is some sensor collect data, is it? But you need to clean those data before you can start processing. Is it? Because just think about for web scraping, is it? It's not all data is going to be numbered. Is it? There are some other types of data. Is it? How do we deal with? And sometimes data is missing. For missing data, who remember?
Masking using NP range.
What is that? I'm sorry.
Masking using NP dot range function.
Oh no, not that. Missing data. So whenever you have some data, so now data, how do we deal? We can, if it's not, it's very, very few. It's very, very few missing data, and your data set size is quite large. What you can do? You can starting with D, you can R, we can do what? We can drop it. Is it? We can drop that. Okay, if it's, and your data set won't, so kind of you just drop that sample. Is it? But that's not a recommended way. Recommended way is we do what? We do interpolation. Is it? And generally speaking, you interpolate with what? Using what? Using column mean. Is it? Using all of the samples at that feature, at that column's mean to fill the missing data. Is it? To fill the missing data. So that's general approach. Is it? To deal with missing data. But there is another category of data, is it? Is we call them, they are string, is it? So they are string, so they are, generally speaking, we call them categorical data. Is it? For categorical data, there are two approaches to deal with. Do you remember? One is called imputing. Is it? So imputing is to do what? Is to we have two types for categorical. Is it nominal data? Nominal data. The other one is called, oh, I just forgot that word. Okay. Oh, I forgot that word. So anyway, so categorical data. So one is kind of like called ordinal data. Is it? Ordinal data is suppose like your shirt size. Is it? Your shirt size can be XL, large, and the medium, is it? And the small, something like this. Is it? And for this kind of categorical data, then you can just convert them into numbers directly. Is it? Like this is a 5, 4, 3, 2, 1 something. Is it? Or X is 1 something. Is it? Because they inherently has sorting order. Is this we call ordinal data? Is it? But there's some other type, nominal data. Nominal data is suppose like weather. Is it? Whether you have sunny, is it? You have raining, and you have cloudy. And for those, there is no order among them. This is not sunny is going to be 3 better than rainy is 2. Is it? Because if you just apply 3 to 1, then when model doing the training, it will inherently think that it has some, so the numbers order plays role, but actually it doesn't, is it? So we don't apply this approach. That's not good, is it? So we apply approach. Do you remember there is approach called one hot encoder? Is it? One hot encoder. Who still remember how one hot encoder works? How that one hot encoder works for nominal data? One hot encoder is to do what? So to achieve one hot encoder, there are 2 approaches we can do. Is it? In sklearn, you can directly use one hot encoder. Is it? And it will take care of that. And in pandas, you can also call the method called get dummies. I get dummies. Is it? It can also directly do one hot encoder approach. So what is called one hot encoder? It's what? It's you are going to, because initially this is a single column, is it, called weather, is it? Then you can have sunny, rainy, or cloudy. Now you are going to convert this single feature to what? To 3 feature called weather sunny, is it? And weather raining. And the 3rd feature is called weather cloudy, is it? And with these 3 columns, 3 features, what are the legitimate, generally speaking, value, the numbers? They can take. Is it still 1, 2, 3, 4, 5, those numbers? Who remember that?
Uses binary values.
Yeah, very good, very good. Yeah, you can put that. So either 0 or 1. As you can send to the chat. Is it either 1 or 0? Is it either 1 or 0? Is it? Then the question, can you have one row both at 1? In one row, you can have 3 of this column, or 2 of the column, or have 1. No, is it? Because it's either sunny or rainy or cloudy. Is it? Can only one of these 3 be true? Is it? But you can have multiple zeros, but not ones. Is it? So this is called, this is for nominal data pre-processing cleaning. Is it? We can apply this. And what did I see for the other? Oh, okay. Data pre-processing regarding, that's regarding missing data, categorical data. And then we also discuss here, yeah. standard scalar? Is it from sklearn, pre-processing? Is it? So generally speaking, what is the goal? Why we do this standard scalar? So what's the reason behind this? The reason behind this scalar is for what? So data pre-processing, one of the other thing is we do scaling. Is it? So the reason to do data scaling is for what? So we can bring. Oh, sorry. Oh, it's already 9:55. I have another class needed to go. Okay, we haven't started this example, but this example is pretty straightforward. Okay, so there is, so basically we are done with this